All right, welcome. Today I wanted to give a brief introduction on one potential way to speed up level generation as well as level building in your game project. Today, the method we're going to be looking at is utilizing image parsing and level generation. This method allows you to use images that you've drawn in various programs to generate the levels instead of having to write the code manually, which we did the first time and realized that it was better to explore possibilities and spend time building out a tool such as this to speed up your process significantly. So what is the goal of image parsing and level generation? This allows us to use a more visualized method to build our levels. Something like Excel also works, but personally for me and our group, we found that using images drawn in something like Paint, Photoshop, or any other image editing program worked better and allowed us to very quickly put together levels. This allows us to save time writing code. Even though the tool itself will take some time to put together and to customize for your project, it will save you significant amounts of time as we have already found with our team. And it makes modifications to the level easier as it avoids having to do manual math to determine where things should go and allows the parser to take care of that. So the workload that we had for Sigma Grind. Previous to the implementation of this tool, our workflow consisted of writing a line of code in the level, running the game, playing through the level to find it, adding the next line of code, repeating it, and fixing any mistakes that we had along the way. This involved a lot of manual labor, it involved a lot of math, which even though it's alright to do, after 4, 5, 6 hours, it definitely gets tedious. So with the parser, our workflow became opening a drawing program such as Paint, using a brush tool to draw in the level, and draw in all the entities that you wish to add. You then can run the parser and play the level as you drew it. This speeds it up considerably and allows you to do things that sometimes would take very long amounts of time to do by hand, such as spherical objects or anything like that, which would require A, a lot of math, and B, a lot of distinct lines of code to implement. So how do these two workflows compare? I noticed that after building this tool, I was able to build a level 2 times the size of our first level in about 1/3 of the time. The first level took about 7 to 8 hours to put together. The second level took about 2 to 3, which is still a significant amount of time, but you can see that the compared amount of time is very different and is significantly more manageable for larger amounts of level. So how does this work? This version of the parser was built using Node.js as that's the framework that I am most comfortable with working, but this can be done in any language and utilizing any image library that allows for image parsing. This can be done in Java, can be done in C, can be done in C++, or anything else. This allows us to parse the image and allows us to work with it. For this, I utilized a NPM library called Jimp, which stands for JavaScript Image Manipulation Library. This handles parsing the image into a format that we can work with. Instead of having to manually figure out how to read in image file formats, Jimp allows us to access them in a form of a 2D array using its image parsing under the hood. So for this, we're going to be utilizing the PNG file format. And I think it's great to give an overview of what PNG stands for and what really goes into this file and to help us understand what we're working with. PNG stands for Portable Network Graphics. A PNG file is a raster-based image rather than a vector-based image. Looking at the visual on the right, we can see that vector-based images are using anchor points to create smooth lines that are very scalable, while raster images are built on individual pixels. And this pixel representation is what will allow us to work with the image parsing because we can have access to exactly what pixel is at which location in the image, we can gather the data from it, and we can utilize that to parse out our level data. PNG was initially created as a replacement for the GIF format, and I will stand by the fact that it's pronounced GIF, and you can feel free to tell me why I'm wrong in the comments. And another very interesting thing about this format, as I'm sure we're all very familiar with, but it supports transparency in the image. So unlike other popular formats like JPEGs, PNGs do support transparencies in the image. So what does this overall workflow look like? How can we go from something we drew to something that we can play? I've created a basic representation of how this is going to work. Up top left, we have an example image from a level built for the Sigma Grind game that we are working on. We pass that image into Jimp and let it handle all of the processing. Jimp then allows us to access it as this matrix of colors and matrix of pixels. Here we can see representation that isn't from this level, but it's a great visualization of what happens. We then allow the parser logic to take control and to read those pixels and to really determine what needs to happen from there. Afterwards, it spits out code that we can plug directly into our game, have a level. As you can see, we can see the full health pack that we see in the top left, we can see the player in the middle, and we can see the dog that's represented by the pink pixel. And in the end, we have a lot of happy children who now get to play a game that was created using this method rather than spending significantly more time to do it manually. So let's get an example of this. So moving on, we can see I have Photoshop open as my program of choice, and I also have the color coding key that was created. Because the parser will be looking for specific color values, it's great to have a color key designed like this so we can always have access to our values. So let's go ahead and make some changes to this level. What we can do is, let's say, remove some of this ground, give this a bit of an overhang, make a little bit of a hill here. This will allow us to demonstrate that the image parser really is working. Let's go ahead and also add something like a full health pack right here at the top of the hill. And let's go ahead and take the player object and move the player to the bottom of this hill right here. The dog is also going to be in midair, so we're going to go ahead and remove the dog. And let's go ahead and add a drill entity right up top here. So this image is going to be what our parser sees when looking at drawing our level. We're going to go ahead and save this image, and we're going to make sure to save it as a PNG file. We can call this demo for video. And we're going to save this as a PNG. So this is all we need to do from the image editing side, and our level is pretty much built. So I'm going to confirm and save it as a PNG, and then go ahead and open up the parser file. This is where I'd like to explain some of the logic of how this works. A couple interesting notes to make regarding the way that Jimp handles image processing. First things first is the image is not indexed like a normal 2D array, but like a game canvas that we're used to working with in our game, with 0, 0 being top left and y positive being down. And pixel at index 2, 5, unlike a 2D array which would be on row 2, column 5, it's inverted. It's stored at column 2 and row 5. So the first coordinate is the x coordinate and the second coordinate would be the y coordinate. So here I have some constants defined for the separate color values that our game uses. These color values match to what we've seen on this color key and allow the image parser to match the color values here to things in our image. Down here, we can store a couple things. The image name, which is going to be the image that is imported into our game. We can name this demo for video. .png, and making sure to specify the file format. I will also name the actual level function load test level. And this is where some of the magic begins to happen. We have Jimp read on our file, we grab its width and height, and then we just use a nested for loop to iterate through all of the pixels in the image. We're going to iterate through every pixel and check its color value. I'm doing this utilizing a switch statement right here, which pretty much just checks the color value using getPixelColor at the x and y coordinate. And then it checks in the switch statement to see if it's any of the tiles that we've worked with. So ground tile, player tile, metar, drill, spike, and so on and so forth for any other entity that you might want to add into your game. And having found any of these, it's going to call the appropriate generate method. These methods, for example, generate player. What they do is update the pixel color to all zeros, which is transparent, which just allows us to better see what pixels our parser captured and what it didn't touch. And then it adds the appropriate line of code to the array of commands that are going to generate our level. For example, here we have game engine add new player, and it passes in the appropriate parameters to add a player to our game. After doing this for every pixel, what we do is add some filler code for Sigma grind to make sure that the level is complete, some functions that we need to run before the player gets to actually play the level, and it also, using the level.write function, creates a new image called updated test image. What this allows us to do is see the final result of the image and what was actually parsed out. So having updated the path for our image, we can go ahead and run the parser. As we can see, it found ground, 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 spike, ground, the health pack that we added, found the dog that we added, and now we can look at our updated test image and we can see the things that it found. We can see that it found the ground, it removed all the ground, it found the health pack, though this does look to be an outdated version of our level. We can see here the image that we're supposed to be working with, and it looks like I might have not saved the file. So after saving the file, we can then see that it added the drill, we can see that it added the health pack, the player, and looking at our updated test image, we can see that all the transparent areas are what it found. So looking at this, we can see that it's pretty much a perfect match to where we had entities that we wanted to add. Then, in the parser, I just have it writing to a text file down here using the fs library for file writing. Looking at levels.txt, we get this really long string of characters. But this string of characters is exactly what Sigma Grind is intended to understand. So going into test level, we can paste it in, and utilizing using document formatting, we can see that this is the output of our parser. This seems like an insignificant amount of code. However, if you were to do this manually for a larger level, it would be a lot more time consuming. So going ahead, we can now go into Sigma Grind and run the level, and it spawns us outside of the game. What a great start. So let's go ahead and place it, and let's see what we have here. So we can see our box that's sectioned off, we can see the spikes that we placed down, and we can, interestingly enough, not be spawned inside of the level. Let's see why it's doing that. What have we placed down in our image here? I think the reason that it's not spawning us in the level is it's spawning us in the ground because we placed the player right on the ground there. So if we move this down to -11, we can go ahead and rerun the game and spawn inside the level. So here we can see the health pack that we placed, we can see the spikes that we placed on the ground, and then moving up here, we can see up here the drill that we also added into the game. And all of this was done by the parser automatically after being given this image. And this scales significantly when you do it for larger images. For example, this is one of the levels that we drew, which took about 2 hours. And as you can imagine, this would have taken a significantly longer amount of time had we done it manually. But now the parser takes this level and converts it into what is essentially 140, 150 lines of code, none of which had to be written manually. And this is why this is a great way to potentially speed up your game design and have the level building process more or less automated for you. And thank you for watching.